Hello, everyone. My name is Abby Bauer, and I'm an editor for Horde's Dairyman magazine. And I'd like to welcome you to our monthly webinar series. We are broadcasting here from Fort Atkinson, where it's a rainy day here in Wisconsin, but we did need some rain, so we'll welcome some of that moisture. The title of our webinar for today is Estimating Energy Supply and Requirements of Dairy Cows. And our presenter is a friend of our webinar series who has been with us before. His name is Bill Weiss, and he is a professor emeritus from the Ohio State University, from the university where he retired earlier this year, but is still doing some work in consulting and keeping busy in the world of nutrition. We look forward to having Dr. Weiss talk to us about methods to estimate energy supply and energy requirements in dairy cattle rations. Our sponsor for this webinar is QLF, Quality Liquid Feeds. We are very grateful for their support of today's program. My co-host is Mike Hutchins, a professor emeritus from the University of Illinois. And our other team members include Jim Balt, our webinar producer, and Patty Hurchin, our online media manager. If you're listening to the presentation live, you have access to the PDF of the handouts of the slides. You can find that in the handout section of the GoToWebinar control panel. Also, if you have any questions that come up for Dr. Weiss during the presentation, please type them into the questions section, and we will answer those following his presentation. At this time, Mike, if you would please take a few moments to further introduce Dr. Weiss, and then we will get started with this month's webinar.
Well, Abby, thank you very much. And it is my professional and personal pleasure to introduce a really good coworker and friend of mine, Dr. Bill Weiss. As you mentioned, he is professor of dairy cattle nutrition emeritus at The Ohio State University with over 30 years of service there, serving in a joint research and extension appointment. Dr. Weiss earned his bachelor's and master's degree from Purdue University and his PhD degree from The Ohio State University. He then had a short period of time as assistant professor at North Dakota State University before joining the Ohio State staff in 1988. Bill is a prolific writer with 140 Journal Plus reviewed articles, over 450 conference proceedings, and he has received numerous awards from the American Dairy Science Association, including its prestigious Fellows Award as well. Some of you know already that Bill was on the 2001 Dairy NRC Committee, and he is co-chairing the 2021 Dairy NRC, which we'll be hearing more about probably in the next 3 or 4 weeks. So, Dr. Weiss, we welcome you back to the webinar series here, and we'll turn the program over to you.
Thanks a lot, Mike, and thanks, Abby, and good afternoon from a overcast Cincinnati, Ohio. Okay, today we're going to talk about energy, and I want to make this a little bit historic because I think a lot of people have forgotten how we actually came up with this energy system. I think you need to understand the basics as you get into how we're actually going to apply this. And we don't measure energy, we measure heat. And that we measure heat because 100 years ago or 120 years ago, when we started this energy nutrition stuff, that's what they could measure. And so the primary instrument we use in energy metabolism in a dairy cow is a bomb calorimeter. And you can see that doesn't look anything at all like a cow, but that's what we have. And so there's some issues with using heat. It works, but you just have to realize that there are some issues with this method. One issue is that just because something that produces heat doesn't mean the cow can get 1 iota of energy out of it. If you take an average cow here, producing 80 pounds, she's going to digest, if she ate uniformly across the day, everything's uniform, every hour she'd digest about 1.8 pounds of dry matter. And that 1.8, if I put that in a bomb calorimeter, it's going to produce 3.6 megacals of heat. Well, I could feed that cow that 0.8 kilograms of plutonium, and for the rest of that cow's life and many lives afterwards, it's going to produce almost 250 megacals of heat every hour. If I feed that cow gas, 8.8 kilograms of gasoline, that's going to produce 9 megacals of heat. And of course, a cow can't use gas or can't use plutonium. And there's other feed substances that the cow cannot extract energy from, but it still shows up as energy in a bomb. For instance, urea. Urea, the cow gets no energy from urea, but it shows up as heat. And so there's some issues with it, but by and large, the system we have works. Just realize there are some limitations. The cow is basically a machine, just like us, and machines take energy in one form and then transform it into other forms. And basically the only energy input into a cow, they get a little bit of radiant energy from the sun, but pretty minimal, is chemical energy in the diet. You can see all the substances here that, you know, if I take starch and burn it up, it's going to produce so much heat. And if I take fat and burn it up, so much heat, and so on. This is all chemical energy. So the cow gets this, eats this chemical energy, and then she transforms it. And the fact it's transformed is important, because that you have to remember a basic law of physics is that anytime energy is transformed, there's an inefficiency. Nothing is ever done with 100% efficiency. So when this cow transforms energy, they produce heat. And that's an important inefficiency of our system, or of biological system, sorry. This cow takes dietary chemical energy and converts some of it into chemical energy, different forms. You know, fiber gets converted into milk and starch gets into milk, so on. The fetus has energy, that's chemical energy. It's going to produce a certain amount of methane, that's chemical energy. Manure, chemical energy. But in addition to chemical energy, this cow also transforms diet energy into mechanical energy. She has to walk, she has to chew, her heart has to beat. And then lastly, she produces a lot of heat. And this heat is two forms. One is just the normal work. For example, when a heart beats, that's going to show up as heat. But also this inefficiency, this transformation of energy produces inefficiency. And this is a huge loss of energy, as you're going to find out as we go through this seminar. So with that, I'm going to stop here with a very basic question, and then we'll get on to the seminar.
Well, very good, Bill. We now have opened the polls up, so now all of the attendees can vote. And it says, what is net energy lactation, parentheses, NEL here? And you have four choices. The first choice is the total energy in a diet. Heat when completely combusted, that's your first choice. Second choice, energy in a diet that is used to produce milk. The third choice is energy in a diet that is useful to the cow. And the fourth one is developed by professors, such as Dr. Bill Weiss, to confuse us as students. So that's your four choices, and the polls are now open, and we are getting pretty close to 50% of you voting here. It looks like the rain has slowed down the voting in Wisconsin and the cloud cover in Ohio. But anyway, we're off and running here, and we're at, looks like we're at about 67%, Jim. Is that right? Looks like. Okay, let's close the vote. We're going to close the panel now. You have to vote quickly here. And the answers, Bill, here we are. You can write them down if you wish. 5% said total energy. Another 77% indicated energy that's used to produce milk. Abby, we didn't give you a chance to vote here. Anyway, the third choice was energy in a diet that's useful to the cow, 17%. And then 1% of them were feeling bad for you, Bill, and said you're just trying to confuse us, 1%. So the numbers were 5, 77, 17, and 1%. What's your take?
Okay, well, first of all, as someone who's had to teach energy for a long time, I think probably the last answer is more correct than we think. But the right answer, and I would ask this question for important reasons, because we have to understand what NEL really is. And it's not the energy to produce milk, that's part of it. But it's actually the energy in a diet that's useful to a cow. It doesn't matter if that energy is going to be used to produce milk or produce a fetus or to maintain the animal, but it's the energy available that's has use to the animal. They call it NEL because it was developed for dairy cattle, and it has to do with some efficiency calculations. But it's much more than just the energy to produce milk. And this is the scheme that basically shows it. The gross energy is the energy if I take a feed, put it in a bomb calorimeter, burn it up. Total energy. We feed it to a cow. Part of that energy is going to end up in feces. The rest is called digestible energy. This digestible energy then gets into the cow. Some of that digested energy is excreted in urine, mainly through nitrogen compounds. And then some of this energy, this is lost in the rumen, but some of this digested energy is lost as methane in the rumen. And that leaves us with what we call metabolizable energy. And this is the energy that gets to a cell. So all the losses have been accounted for. Now the cell can do something with this energy. But if you remember, I said whenever a cell does something with energy, there's inefficiency. And so it's going to produce something, and it's also going to produce heat. And this heat, which is variable, is called heat increment. And once we subtract that, we're left with NEL, and that's energy that can be retained in milk or growth or fetus. It's energy that can be used for the cow to walk around with, and it's energy that the cow uses to live. So it's all the important productive functions of a cow are based on NEL. So how much losses are we talking about? Well, if we look at the gross energy, which again is the total energy in a feed, urinary energy average about 3.5% of the energy a cow eats, with a reasonable range, not a huge range, but 2 to 6%. Excess protein diets are going to be up around the 6%. If you do a really, really good job on balancing crude protein, it's going to be down around the 2%. Methane averages about 5% of the energy lost. Again, a reasonable range, you're going 2 to 8. We're going to talk more detail in a minute. The 8 is for high fiber diets. The 2 is for high starch, high fat diets. But the two biggest losses of energy is the heat increment, which averages more than 20%, and indigestible or fecal energy, which is a third. The heat increment we think it's this variable, but it's very, very difficult to measure this. So this variation includes cow-to-cow variation, measurement error, etc. This isn't specifically variation caused by the diet. Fecal energy ranges from, or again, this is indigestible energy, ranges from about a 25%. So this is a highly digestible, lower fiber, high starch diet, up to more than 40%. This would be low quality forage, straw-based, etc. This does represent diet variation. So fecal losses are huge. Heat increment is also big. The other two are smaller, but still significant. So if you add all this together, of the energy a cow eats, only about 1/3 of it actually is used by the cow for something useful. Only about 1/3. Measuring all these losses are really, really expensive, and they're hard to do. This is a picture from our research center. This is what we do to measure digestible energy. We measure all the energy the cow eats. Manure, feces drop down here into a container. We measure all the energy in feces, get digestible energy. We have to keep urine separate from feces, otherwise the energy in urine would show up as indigestible. And this is expensive, but again, all we're getting here is DE. If we want to get net energy, we have to put cows in things like this. These are respiratory chambers, so this would hold 2 cows. We put the cow in, we measure all the energy in the feed, all the measured energy in the feces, the milk, etc. And they also collect gas. So this thing is gas exchange. It measures the oxygen, the carbon dioxide, and the methane. And with that information, they estimate how much heat the animal is producing. And again, this is only 2 cows. So think of what it's going to cost to do enough cows to get good energy values. Very, very difficult. Which is why you always get estimated energy. You're not going to ever get a measured energy value from a lab. You just can't do it. So the system we use, and there's very different equations, different models, but this is the basic approach all software uses. They estimate the digestible energy of the feeds, and they use nutrients or kinetic analysis, but of the feeds. They put in equations that based on intake of the cow and the composition of the diet, which affects digestibility of feeds, and they end up with a diet, DE. And from this step down, it's all diet. Feeds do not have ME. A diet has an ME. Because if a feed had an ME, think of soybean meal with all that protein. It's a lot more than a cow needs. That would all end up in urine if all you fed was soybean meal, which of course we never do. So we have diet energy values here. So we calculate diet DE. We use equations, and then we've got some new approaches, which I'll talk about, to get an ME for the diet. And then we use equations to get a net energy of the diet. So measurements based on a composition of the feed, some other equations to end up with diet NEL. I am not going to go through equations. So they're in the handout. I'm not going to do that. It's boring as sin, and I don't have the time. What I want to point out, though, is in 2019, well, several years ago in the 90s, we developed an equation at Ohio State, which had been used quite a bit. It was adopted by the NRC 2001. But in 2019, we reevaluated this. We had a bunch of new data, and we said it's time to reevaluate it. And the changes here are shown in red, and that's all I'm going to talk about. One change was how we use in vitro NDF digestibility. I'll talk about that in detail. Another change was we got rid of NFC, non-fiber carbohydrate. That was in our original equation. But now we have starch and this fraction we call residual organic matter. I'll get into that in a minute. We modified the digestibility for fatty acids, and then we modified the way we calculate this term called metabolic fecal energy, which because of time, I'm not going to go into that. But we did make significant modifications, and the hope of all these modifications was to make the equation more accurate over a wider range of diets. The fatty acid adjustment was dramatic. In the original equation we had, and in the old NRC, fatty acid digestibility was at about 92%. This was based on very, very limited data, because back in 2000, no one measured fatty acid. We measured crude fat. With the emphasis of Don Palmquist, or the impediments of Don Palmquist, he convinced the industry we need to get rid of crude fat. Let's get to fatty acids. And so over the past several years, lots of experiments have been published measuring fatty acids. This is just our data. There's a paper out of Wisconsin, similar type of analysis. They got almost the exact same number as we did. So I think the number's right. But we measure digestibility. We do this test this is a Lucas test. It's not important. But with this Lucas test, the slope is equal to the true digestibility. So with this new data set, the true digestibility of fatty acids averaged 74%, not 92%. And so you're going to say, boy, that's a huge decrease in the energy of fat and from feeds that contain a lot of fat. Well, it is. With these new equations, high-fat feeds will have less energy, less estimated energy today than they did using the previous equation. But it's not as big a change as you think, because previously we had this high digestibility, but the equation also had a negative intercept. So we multiplied the fatty acid by this, but then we subtracted values. With the new number, there's no intercept. So it's a smaller digestibility without an intercept, but it's still high-fat feeds will have less estimated energy using the new equation than the old one. But again, it's not as dramatic as it looks. The Nfc fraction. Again, it used to be Nfc with a constant digestibility of about 92%. We now take starch and then everything else, which we call residual organic matter. This has sugars and waxes and acids, etc. The benefits of this is, one, it's a much smaller fraction. So if we're wrong on digestibility, it's not as big an effect as when the fraction was 40% of the diet. Starch is now routine. 20 years ago, it was not. And there is a large database on starch digestibility. So on the ROM, this again is this Lucas test. It averages digestibility of 96%, and it's a pretty good fit. So there's much to be gained here by, you could measure the sugars and you could measure the acids and everything else. But from an energetic point of view, it's probably not necessary. This is probably good enough. So we've got a one fraction with high digestibility and pretty constant digestibility. And then we have this starch. This again is just our lab. There's 77 different diets, and these are not cow numbers here. These are diet means. So this reflects going from 83% digestibility to more than 95. This doesn't reflect cow variation. It reflects diet variation. Average was 92%, and that number has been gotten by almost everyone. 92% average digestibility of starch by dairy cows is an extremely good number. So the mean is fine, but what's important is we have diets that are 83% starch digestibility, and we have diets that are 95. So just doing the mean isn't good enough. We lose a lot of variation here. And what the degree of this variation, if you again look at this here and here, half the diets in our data set had more than 2% error in DE, just because of starch digestibility. If I use the average rather than the actual starch, that's equal to about 3 pounds of milk, the energy in 3 pounds of milk. So it's significant. By incorporating variation in starch digestibility, you capture a lot of important variation for the diet. The problem is we don't have a way to estimate this. The labs right now, they can offer starch digestibility assays, but these have not been calibrated or evaluated on its ability to predict in vivo digestibility. So we really do not have a lab method. But we do know lots of things that affect starch digestibility, so we can kind of what I call semi-quantify these effects. Particle size is a biggie. This is particle size of dry corn, an individual experiment. And with Dent, which is the corn we feed in the US, basically for every 1,000 micron increase in mean particle size, total track starch digestibility dropped 2.6 units. If it's semi-flint, which is a very hard corn and more common in South America, the effect is even more dramatic. So bigger particle sizes really become much, much less digestible. On this set of the slide is data from a meta-analysis where they categorize different diets based on particle size of corn. And you can see a pretty similar response, again, between 1.6 and 4 units in digestibility, loss of digestibility, for every 1,000 microns. So we can, if you measure particle size, you can put it into these equations. We can get an estimate of the starch digestibility from corn grain. Corn silage is much more difficult for experimental reasons. When we feed diets, the starch in corn silage is only going to make up 20 to 30, maybe 40% of the starch in the diet. That means to estimate starch digestibility from the diet, I have to estimate the starch digestibility from what I'm calling the basal ingredients. And if my assumption is wrong here, that makes the calculated starch digestibility estimates wrong. This is an old study from Randy Shaver. He harvested one hybrid. I can't remember which hybrid it is, from early Dent up to black layer. You can see the dry matter percents of the silage. He measured total track starch digestibility, and then I calculated the digestibility of the starch from the corn silage, assuming 92% digestibility for everything else, which may or may not be correct. But look at the variation here. The very immature corn silage had 94% starch digestibility. The mature corn was only 88. And again, this is a significant amount of variation. Unfortunately, we don't have ways to estimate this other than just maturity, which again is likely, these numbers likely will be dependent on hybrid. So we have these things called kernel processing score. This actually is correlated to total track starch digestibility. We need more work on it, but basically better processing scores is indicative of better starch digestibility. We might eventually be able to estimate starch digestibility from dry matter, and that's what the old NRC did, was basically dry matter was a proxy for maturity, and the drier the corn silage got, the lower the starch digestibility was, and hybrid clearly will have an effect here. So our ability to estimate starch digestibility from silage is still a weak spot of all these equations. NDF digestibility, real quick here, there's lignin-based equations, there are kinetic-based equations based on rates of digestion, so on, and there's in vitro, single time point in vitros. What I want to talk about is the in vitro, use of in vitro. In the old NRC, it stated incorrectly, I might add, and I wrote it, so I'm taking the blame. It said you could use the 48-hour in vitro as an estimate of in vivo, even though we have known since at least 50 years that in vitro does not equal in vivo. This is a study out of Wisconsin a few years ago. They looked at in vitro NDF digestibility. I'm showing 48-hour here because that was the time point that had highest correlation to in vivo, which is really important here. If we're going to correlate or look at these things, we need to say, can it actually predict what a cow is going to do? And the 30-hour did not. The 48-hour has reasonable correlation. You can see it's by far not perfect, but it's the best we have right now. And this is their equation. And so instead of plugging, if you use, let's use this point right here, instead of saying plugging 45 into the equation, you'd plug 45 into this equation, and you're going to get an estimated in vivo of about 40%. So do not directly use the in vitro number. You did a 48-hour in vitro, plug it into this equation, get an estimated in vivo, and use that number. Okay, I need a drink of water, so I'm going to turn this back over to Mike for the next question.
Very good, Bill. We have another polling question, a chance to vote, and things get tougher now in this voting. Replacing fiber with starch usually increases diet NEL, expressed as mcals per pound. What other things might increase dietary NEL? And so we have 5 choices here. First is to increase the DCAD of the dietary cation difference, slightly restrict dry matter intake, separate 2-year-olds from mature cows, reduce crowding in pens, and the 5th one, which is always a popular one, is all the above. So I think voting's going a little slower here. Abby, do you have? I've got mine picked. Have you picked yours out?
My answer is all of the above. What do you say, Mike?
I'm going to go with number 2. Slight restriction in dry matter intake, but I'm taking kind of swag on that one as well. We've got to almost 60% of the vote in, so hopefully Dr. Weiss has got his water consumed and it went down the right port of the track. Let's close the polls, Jim, and see what the people had to say. Interesting. We've got Abby, you might win this one. Bill, increasing DCAD, 6% voted that. A slight restriction was my vote, about 30% or 29%. Separating 2-year-olds from mature cows, 5%. Reducing crowding, 5%. All of the above, 56%. Okay, Dr. Weiss, you're going to make some people happy, and half people are going to be unhappy.
Well, I want to emphasize the question said might. Some is known, some aren't. DCAD is your increased DCAD and improves digestibility. We know if we restrict intake, it increases digestibility. This can be done with heifers. It's more common. We restrict intake on heifers. We don't practice this for cows. We think, we don't know, but we think doing these 2 things, separating heifers and reducing crowding, what this should do is result in a more stable rumen, less slug type feeding, which should improve digestibility. So I think the right answer is all of the above. I think all these have the potential to increase digestive efficiency. But again, we need research on looking at how management can affect digestibility. This is the old NRC showing the relationship between intake, expected body weight, percent of body weight, and dry matter digestibility, which is essentially digestible energy. And it had a huge effect For every one unit increase in DMI, again, as a percent of body weight, dry matter digestibility went down about 2.5 units. Huge effect. This equation was developed from data where people fed dry cows, and then they fed the exact same diet to lactating cows. So it really is a comparison between a dry cow and a lactating cow, which is the data they had, but that's probably not the best way to do it. A much more recent paper published here a few years ago out of Michigan State found it's still negative. As cows eat more, they digest less. There's absolutely no question on that. The question is, how much less do they digest? And when this study, which is based only on lactating cows, so to me it's much more realistic than comparing dry cows to lactating, the effect was about a third of what the old NRC. So what this is saying is that these cows that eat a lot still are less efficient on a digestive basis than cows that eat less, but it's not as bad as we used to think. So increasing intake still reduces digestive efficiency, but the effect is much, much smaller than previous models. Another thing that affects digestibility of fiber is starch. And this probably has to do with rumen pH. If you eat a lot of starch, rumen pH drops, fiber digestion drops. This is a meta-analysis. And what they found is that for every 1 unit of starch you increase, fiber digestibility, not DE, but fiber digestibility drops about half a unit. So that it still means as I increase starch and reduce fiber within reason, that the NEL of diets will increase, because fiber is 50% digestible, starch is 90% digestible. But the increase in energy isn't as great as people think, because the negative effect on starch. So we can incorporate starch effects, we can incorporate DMI effects. DCAD I'm not going to talk about, but it's basically buffers. You increase DCAD by feeding buffers, which improves digestibility. Okay, the next step in this is getting to ME. And remember, DE is not a good indicator of diet energy. ME is much better. For years, this is the equation. You take the DE value, plug it into this equation, and get ME. But you got to think of what's the difference between ME and DE. Well, it's methane and it's urine. And that's not in this equation. Methane production, the rumen, is a function of digestible NDF intake, which increases methane. The more digestible NDF a cow eats, the more methane. And it's a function of fat. The more fat you feed a cow, the less methane. Urine energy is largely a function of amino acid balance, or it's more than crude protein balance. But if you feed a lot of excess protein, that nitrogen that's not going to be put into milk goes into urine. That's energy. So we now have equations, which I'm not going to go into, that we can estimate methane, we can estimate urine, and we then just take this estimated methane, the estimated urine energy, subtracted from subtracted from DE, and we get, to me, much more accurate values of ME for the high protein diets, high fat diets, etc. On average, this old equation worked fine, but it didn't work. It did not reflect how protein can affect energy availability. Then the last step to get NEL is the weakest link of all this. All we do is multiply ME by a number. You can make an argument, if that's all we're going to do, let's just use ME, but we're stuck with the NEL system for right now. Even though we think, nutrients, supply of nutrients should affect heat increment. We just don't have the equations to adjust that. So just a constant. Okay, one question I wanted to answer specifically is this. There's a lot of emphasis on feeding lower protein diets for both cost and environmental reasons. And I don't want you to leave here thinking I'm saying we shouldn't do that. What I want to leave you with, though, or talk to you about, is that we need to be careful when we do this. Protein does more than just provide amino acids. It has a direct effect on energy. And what got me thinking about this was a paper published a few years ago out of France. This is a little confusing. The numbers here that are on the graph don't matter. This is the energy. 0 was the diet that was perfectly balanced to meet requirements. The negative numbers are deficient energy diets. The positive numbers are excess energy diets for this particular set of mid-lactation cows. On this axis is protein. This is the European system. Just think MP. The 0 meant the diet. This was a diet that was balanced to provide adequate MP. Negative are MP deficient diets, and then the positive is MP excess diets. And I'm only going to look at 2 sets of bars. The very front one here, which is cows fed very protein deficient diets over a wide range of energy supply, and they found no difference in milk protein yield, which is exactly what should happen. This is mid-lactation cows. If there's not enough protein to make milk protein, energy supply shouldn't matter. It should not increase milk protein yield because there's no protein there for the cow to use. So that's makes perfect sense to me. The set of bars that didn't make sense was this back one here. This is a set of diets that are very deficient in net energy. Going from deficient protein up to excess protein. And you'll see that milk protein yield increased, even though these cows are very deficient in energy, and these are mid-lactation. That's important. This happens in early lactation, but in mid-lactation, if the cow is deficient in energy, providing more protein should not translate into more milk protein because they don't have the energy to make it. But in this study, it clearly went up. And so what this suggests to me is that this change in protein is also changing energy supply. Remember, these are estimated energies, which are estimated independent of diet protein. So this suggests feeding more protein actually increases the NEL of diets. Why does this happen? Well, we know, and we've known for a long time, increasing diet protein increases digestibility. This is an old study, and it's a little confusing here, so I want to just take a minute. Along the X is the percent crude protein in the control. Each of these points are an experiment where they had a control diet and at least one other treatment diet that had higher crude protein. So if we take this blue dot right here, the control diet in this experiment was 14% crude protein. The treatment diet had more protein. I don't know how much more, but more protein. But for every unit increase in protein from control, dry matter digestibility increased a little more than 1 percentage unit. So all these, the average for this set of treatments here was for every 1% unit increase in crude protein, digestibility of dry matter went up 1 unit. And you could argue, well, this is because these are low protein diets, they're deficient. Well, they also had some very, very high protein diets, and they see the same thing. The control here at 23% crude protein, adding more protein to the diet increased digestibility. So more protein increases digestibility. Conversely, more protein increases urine energy, which is a loss, and it increases heat increment, which is a loss. This just shows you as urine energy goes up, heat increment went up. So I put all this together in an example where I'm going to add increased diet crude protein by 2 percentage units. And as protein goes up 2 units, starch went up 1 unit, fiber went up 1 unit. So that's my assumptions. So based on the expected increase in gross energy, protein has more energy than carbohydrates, and the expected increase in digestibility, this 2-unit increase in protein would increase DE intake by more than 2 megacalories a day, which is equal to 4 pounds of milk, or the energy in 4 pounds of milk. But DE is a poor measure of feed energy. We have to account for losses. So if I adjust for the increased urine energy loss, this change in diet crude protein is only 1.5 megacalories of ME, which is still 3 pounds of milk. But again, excess protein increases heat production. And we're not very good at estimating this. I'll admit that. But if I use the equation I just showed you, we still are going to, this 2-unit increase in crude protein would still increase NEL intake by 0.6 megacalories a day, which is the energy in 2 pounds of milk. So we need to be careful about reducing protein without thinking about how it's going to affect diet energy. Okay, for the last poll question, I'll turn it back to Mike.
Okay, well, Abby, get your thinking cap on, because I cheated on this one. The question is, interestingly, U.S. milk yield increased 44 pounds per cow per day over the last 40 years. That's an amazing number to begin with. How much did NEL, megacalories per pound of the diet change? So as cows gave more milk, how did the energy change? We have 4 choices: minus 4%. In other words, it dropped. 0, it didn't change at all. It was pretty flat. 10% up, or 20% up in terms of how that changed. And it's kind of a tricky question, Bill. And I think at this point, Abby, do you want to vote, or are you just going to go home with your win for the day, like the U.S. in the Olympics?
Well, I think you're disqualified since you looked ahead, Mike. But these are really challenging questions that I'm going to pick that there's been no change. Really just a guess, but that is what I'm going to go with. I see we have a good participation in the audience, but half the people have voted so far.
Okay, well, that's good. Well, Jim, let's go ahead and close the poll, because our time is valuable. We got lots of questions here. And here we go, Bill. The votes are for a drop of 4%. 10% of the people voted there. 25% were with Abby at 0. 48% said 10%, and 17% said 20%. So most of the people are saying, yep, it changed over those time period. Bill, what's your take?
Okay, well, the important part of this question was the units, and that's density, megacalories per pound. NEL intake has probably increased by at least 20%. But this is energy density, and it is actually what 40 years of research has done, decreased. Cows are less digestive efficient today than they were 40 years ago. This just shows you over 40 years per year, and it's not linear, but per year, digestive efficiency drops 0.07 units. Our research emphasis was on designing diets that would get cows to eat, and we've been very, very successful at that. But again, as I mentioned earlier, if cows eat more, they digest less. And so maybe it's time we start emphasizing in a research area, and I know this is being done, is to start putting more emphasis on metabolic and digestive efficiency rather than just getting cows to eat more and more. So energy intake has gone up. Energy per unit of dry matter intake has gone down. Okay. To wrap up here, I've spent most of the time on supply, but you have to remember there's a requirement system. And this whole energy thing is a bit arbitrary because, again, it's based on heat. And so I just want to caution you that these systems are kind of self-calibrated. They make adjustments in one or the other, so it comes out about right. And so be cautious about using one model to estimate NEL concentration or NEL supply and another system to estimate requirements. You really should be consistent within a model. Use the same model for supply and requirement calculations for energy. To me, the big change in energy requirement over time has been maintenance. The equation we've used for maintenance energy that's been used, I think, since at least 1989, and maybe even before then, was this shown here. And which means a 1,450-pound cow had a maintenance requirement of 10.3 megacalories a day. But over time, we've changed this cow. These cows are leaner. There's more muscle mass relative of the body. There's more organ mass, and muscle and organ are metabolically active. So to me, there's reason to think that maintenance has gone up in today's modern cow. There's been several experiments, and again, this is very difficult to measure, but here's just 3 examples. within an experiment, there's a lot of variation because, again, this is so difficult to measure. But all of these have higher maintenance. Even the lowest estimate from all these papers is higher than this number, and some are really higher. So if you kind of average everything and round things off a little bit, I think current data suggests maintenance is probably closer to 0.1 than 0.08, which in a megacal basis, that means energy is probably, maintenance energy would be about 13 megacals a day instead of 10. What does this mean to cows? In a dry cow, since maintenance is by far the biggest component of her energy requirement, if we would update or change a maintenance requirement to what I just said, it would increase her total requirements 20%. For a high-producing cow, it would only increase her energy requirements 5% because milk is such a big component of the energy needs. For a lower-producing cow, about a 9% increase. And then I compared a Jersey and a Holstein, each producing 70 pounds of energy-corrected milk because the Holstein is bigger. Her maintenance, her total energy requirement would go up 8%, whereas a Jersey would only go up 7%. So I think we are probably underestimating maintenance requirements of these cows, which could have a big effect on dry cows and low-producing cows. And the other things on energy, milk, growth, and pregnancy, there's not much new on this. And what is new supports what we've been doing for a long time. So these requirements probably haven't changed much. So I think the old system probably worked pretty well for pregnancy, growth, and milk production. So to wrap this up, on the supply side, I think we made significant improvements. We've added starch, we've adjusted fatty acids, we've improved our ability to account for the effect of intake and starch, but there's still other factors to add in. This protein fact I talked about, that's not in here anyplace, where feeding protein could increase dietary energy. We've improved our ability to predict ME, which should account for variation in diet protein, diet fat, and diet fiber. I think maintenance has increased and our old equations are no longer adequate, but all the other stuff, all the other needs for requirements probably have stayed or pretty reasonable from the old methods. And with that, I'll turn it back over to, I don't know if it goes to Mike or Gabby or Abby.
Thank you, Bill. I'll take it here for a minute. Once again, thank you, Dr. Weiss, for presenting for our webinar today. We appreciate the way you dug into the topic of energy for dairy cow rations, and we all know how important energy is in having those cows on the farm and producing milk. So thank you for going through some of these methods to measure energy and how it works in our dairy cattle. So thank you. I would also like to thank once again QLF for serving as a sponsor for this webinar. Quality Liquid Feeds. You can find them online if you want to learn more. We appreciate them being a part of our program and sponsoring this particular event. If you would like to view this webinar again, it will be available online on our archives later this week. You can also find all of our previous webinars archived there and go back and check out any of the topics that interest you. You can find those at our website at hordes.com at the webinar tab. We hope you'll make plans to attend our future webinars. They are always held the second Monday of the month at noon Central Time. In September, we'll have a presentation titled Raising Calves on Auto Feeders. Will it work for you? And our presenter will be Bob James from Virginia Tech University. Then in October, we'll have a presentation focusing on ventilating dairy barns. And our speaker then will be Nigel Cook, who comes to us from the University of Wisconsin-Madison School of Veterinary Medicine. So if either of those topics interest you, please mark your calendars and make plans to join us again. We had a few questions that came in, and I want to remind everyone that if you have any questions for Dr. Weiss, you can still type them into the questions section of the GoToWebinar control panel. We have some time right now that we can answer those. So please type your questions in. But Mike, I see there are a few here already. So if you would, can you go through those questions with Dr. Weiss, and we'll give him some time to answer them.
You betcha, Abby. And we do have questions for you, Dr. Weiss. So the first one is kind of long, but it was on my list of questions that I was wondering about as well. And the individual says, why use NEL to represent all net energy? Why not just call it net energy like you do digestible metabolizable energy? That represents mcals available for milk production, but there'd be a different number if it was labeled NEG, which is net energy for growth, or NEM for efficiency of maintenance. And this individual thinks it confuses students. Your take on it?
It does confuse everyone, not just students. The reason, again, we have in the net energy system, there is a net energy for gain. Growth is inefficient. It takes the efficiency of converting ME to NE for growth is much lower. So we have this NEG. A feed will have an NEG number. It'll also have an NEM number, which is essentially the same as the NEL number. So long ago, they decided in growing animals and growing beef especially, they have an NEM and an NEG. In dairy, because growth really isn't a big deal for a lactating cow, and maintenance and lactation were about the same efficiency, that's why they said we're going to call this NEL, just to differentiate it from the beef system. So that it's basically an historic thing. You could argue it should just be NE, but then we still need NEM and NEG for the growing ruminants. In dairy, we typically, for growing heifers, we don't use the NE system. We use ME, which to me makes it's simpler, and I think it's actually adequate for lactating cows. But the reason we call it NEL is simply to differentiate it from NEG and NEM, which is used for other ruminants.
A number of European countries use ME instead of NE. Are they ahead of us or behind us, or what's your take on the system itself?
I think they're equal. I mean, you got to remember our NEL is simply ME times a constant, so they're almost the same number. So I really don't think there's any difference. I think we tend to be fooling ourselves a bit, thinking that we're better because we're accounting for heat increment, which we are, but we're not accounting for any variation in heat increment. So to me, just to be a little more academically honest, we should just stick with ME and realize that the ME, there's still going to be a lot of waste energy at the ME, but if all we're doing is multiplying by a constant, we assume heat production is the same for all diets, which it isn't. We just don't have the ability to estimate it. So either one is fine. I'm switching much more to using ME just because it's easier and it does the job.
Okay, another question came in. Could you talk a little bit more about processing corn silage, conventional versus kernel processing regarding into milk and digestibility? So in other words, if I had a kernel processing score 75 versus say 50, could a model not take that into consideration?
It can, and I'm afraid I can't give you the coefficient. I can't remember, but there's been at least one study where they took different kernel processing scores and compared it to in vivo starch digestibility, which is again is what it needs to be compared to, and there's a correlation. And I just can't remember the equation. So that to me would be the first bet, or to use that, and that will adjust for kernel processing. Dry matter may or may not be all accounted for in that analysis, but I think that's a place to start, and then put in maybe some adjustment for dry matter. But there's going to be some guessing and some swagging for estimating starch digestibility of corn silage. It's difficult to do, but I think kernel processing right now is one of the best methods we have, but it still has some error, and it's still going to be somewhat dependent on hybrid.
A related question, and that is, if maintenance requirements are underestimated, as you indicate, does that mean that we are also underestimating the efficiency of use of metabolizable energy for lactation?
Yes, we are. And one thing I didn't go into is that efficiency number we use 0.66 for ME to NEL is different than it was in 2001. They reanalyzed the same data with better statistics, and the efficiency is higher than they thought. So some of that gain or some of that increase in maintenance requirement won't actually show up in the energy balance calculations, because the NEL of diets are all going to be a little bit higher because of this higher efficiency. But yeah, all these things are correlated. And so if I just said maintenance went up without discussing efficiency, you're only getting half the story. So maintenance goes up, but not as much as it looks like, because feed also will have more net energy than it used to because of a higher assumed efficiency.
Another related question in terms of fat, and that is, since most of these fat products now have fatty acid composition, saturated, unsaturated, 16-1, 16, 18, 18-1s, could a model predict a different value than just a flat 74% as far as fatty acid efficiency?
It could, that 74% is for basically diets without a lot of supplemental fat. And so I think it's a good average number for basal diets. If you're getting a supplement, say that's high in palmitic or palmitic or high in oleic or whatever, then these different coefficients could be used. And there are equations based on chain length and saturation, so on. But that 74 is really for basal ingredients, for diets. Individual fat supplements would have different numbers based on, the numbers I use are based on experimental results. But I think you probably could use fatty acid composition to come up with an estimate for the supplements. I don't think it's really that important for basal diets, because I don't think it's going to vary enough to have a big effect on fatty acid digestibility of basal diets.
Another related question was, you mentioned dietary fat reduced methane production. Is that related to unsaturated fatty acids or all fats?
The experiments where they measured this, it was just total fatty acids. And part of it is, carbohydrate digestion in the rumen generates some methane. So part of it's that. There might be a little depression in fiber digestion with fats, which really doesn't show up too much when we look at all the data. So I think mostly it's because fats are not fermented extensively in the rumen and don't produce methane. They also can act as a hydrogen sink and again reduce the need to produce methane. But and theoretically, the polyunsaturates should be a little bit more, but I don't think it's enough to matter on methane production.
Okay, a different kind of question. How fine should we be grinding flint corn for our colleagues in South America and probably Mexico?
There's a trade-off. You cost more money the finer you grind it, but when you look at the studies, I'd say in general for dent, you're at 1,000 or less, you're probably fine. For flint, I'd probably be closer to the 500 microns.
Okay, that's a good answer. Next question. Does it mean that if silage is has low digestibility, in other words, high UNDF, would you add more protein to correct for that? More protein, more digestibility?
That's a good question. I'm going to say I don't know. I'm going to give an opinion here, but I don't know. But in general, when you look at these studies, especially the old studies, they would be not what we would consider high quality diets today. The forage quality generally was worse than what we feed today. Not specific to corn silage, just forage quality in general. And a lot of these older studies saw a significant increase in digestibility with crude protein. So I would say I tend to think that increasing crude protein would have a bigger effect on less digestible diets than on highly digestible diets. But again, that's opinion, not fact.
Okay, one more question, a couple more questions actually. For the relationship between dietary starch and NDF digestibility, is this relationship due to replacing highly digestible fiber sources with starch, or is it the effect of starch on fiber digestibility in the rumen? Did I confuse you on that?
No, it's probably, when you look at the way these equations or experiments are done, especially that meta-analysis, it's likely an effect of an effective starch on bacteria within the rumen that's going to affect fiber digestion. Feeding more starch, especially if it's fermentable, reduces rumen pH. That changes the bacterial population, reduces fiber digestion. So I think most of that, because again, it's across a bunch of studies, it's likely mostly a ruminal effect on bacteria, on cellulolytic bacteria. And this has been known, you can dig back through, I'm going to say at least 50 years ago, we knew overfeeding starch reduced fiber digestion.
Okay, we have 2 more questions, but they still keep coming in. Several said, thank you very much, Dr. Weiss, for the information and fine webinar. I concur. You mentioned the reason for higher maintenance estimate is due to a leaner genetic type animal. Do you have any data to support this difference in composition with older genetics? And then the other comment, if so, would this difference in composition affect the efficiency of ME for growth?
The first part, I don't have a lot of data for cattle. There are data with other species, dogs, pigs, and I think even humans, that leaner animals have higher metabolic, what we would call fasting heat production, which is essentially maintenance. And there's been people suggesting that body condition score should go into these equations. There's not enough data, I don't think, to do that. But to me, the concept, there's enough data supporting the concept that fat animals per unit of body weight have lower maintenance than thin animals at the same body weight. Again, with ruminants, the data isn't as strong. I can't remember the second question or the second part, Mike.
Okay, we're going to try to bring that back up. The second part was, would this difference in composition affect the constant for efficiency of use of ME for growth?
Yeah, definitely. And if you look at beef equations, which put a much bigger emphasis on growth, they will actually try to predict the composition of that gain, and then the efficiency of converting ME to that gain. For example, if they're gaining a lot of protein and not a lot of fat, that's an inefficient process. If they're gaining a lot of fat and little protein, that's a much more efficient program or process. So a lot of the equations, again, and especially in beef, estimate estimate the composition of the gain that's based somewhat on the age of the animal, the size of the animal, and lots of other things, and they adjust the efficiency accordingly. And there's no reason that couldn't be done with dairy if we can predict the protein and fat in the gain.
How do you foresee the future use of feed additives, garlic, for example, some of the essential oils, seaweed, ionophores, to improve feed efficiency and therefore, and also via the reduction in greenhouse gas emissions for lactating cows? Should that be put into our models?
Yes, they should. They got to be data, of course. But like for rumensin, there's so much data on that. We know about how much that efficiency is going to increase. That could just be, if you feed monensin, efficiency goes up X amount. Whether that's at the DE stage or the ME stage or the NE, we don't exactly know, but that's not, to me, not that important. It's just that the final available energy would be changed if you put this additive. So if there's data on let's say yeast or these essential oils or whatever, if there's data showing increased inefficiency, and we have to separate efficiency from intake. If there's adequate data to support that, then just say, I'm making this number up totally. With essential oil, we increase the available energy, whether it's ME or NE, by 2% if you're feeding it, and something like that.
Last question, and that is the 7-hour in vitro starch digestibility that's available through commercial lab. Do you see any value, therefore, in using this number?
I'm going to say not for predicting diet energy, because again, I have not seen data, and we've looked at this some in our lab. correlating that or using that number to predict total tract. And I want to emphasize energy is total tract digestibility. That 7-hour might have a value in, you know, balancing carbohydrates in the rumen, preventing acidosis, et cetera, maybe to predict microbial protein better. But to predict the energy from starch, I don't think it's of use right yet, because we just don't know. We know there's a whole lot more variation in rumen digestion of starch than total tract. They're correlated, but there's a whole lot more variation. And this 7-hour, I think, is much more reflective of rumen digestibility than total tract.
Okay. Here's our last question, just came in. Quick comment. What do you think about fibrolytic enzymes for lactating cows?
It's this. There's a fair amount of data. A lot of this is out of Canada showing increased digestibility. And again, if there's enough data for specific products, you would either say, okay, if I feed this, I'm going to increase. I'm making these numbers up, obviously. If you feed an effective fibrolytic enzyme, fiber digestibility goes up 5%. That will change the DE by this amount, the ME by this amount, and so this would be worth. This is the way you could actually price this stuff. This would increase the energy of the diet by X amount. And there's good data showing that at least some of these products do increase digestibility.
Well, Dr. Weiss, you did a yeoman's job answering some very difficult questions. Abby, we'll turn the program back to you to finish up.
Thank you very much. I agree. Thank you, Dr. Weiss, for joining us today for this great presentation and for answering all those questions. We certainly appreciate you sharing your knowledge with all of us during this webinar.
Thank you.
You're welcome. Again, thank you to QLF Quality Liquid Feeds for sponsoring this webinar. We really appreciate their support of our program. We hope that you'll make plans to join one of our future webinars. Again, they happen the second Monday of each and every month. In September, we'll be talking about raising calves on auto feeders. And then in October, we'll focus on ventilating dairy barns. So we hope that you will join us again in the future. Once more, I'd like to thank Dr. Weiss for his presentation. I would like to thank QLF for their sponsorship. And then, of course, all of you in the audience. We really appreciate you spending some time with us. We know we have listeners across the country and around the world listening in all different time zones. So thank you for taking this window of time out of your busy schedules. And we hope that this has been valuable information that you can use on your farms or on the farms that you work with. Once again, thank you from our team here at Hoard's Dairyman and the University of Illinois. And we look forward to hosting you at a future webinar. Until then, take care.